the depth of application and keep the interval constant, or we could actually vary the irrigation frequency and keep the depth applied constant. So there's just two ways of looking at it. Again, all within the context of the constraints of managing a system, especially if it's a sports turf field and you have to irrigate only some certain times. We'll look at some of the newer controller technologies and some resources at the end. So when we go to determine the irrigation water requirement, and in this case, maybe for turf, usually that's based on something we call reference, ET, or evapotranspiration. And the common nomenclature or symbolism is ETO, or ET0, ETO. How do we get that value? Well, we can get it with weather data, and then using that weather data with certain equations to come out with a water requirement and a water use rate, or we can get it from publications. Then once we get that reference evapotranspiration, we need to suitably change that or modify that potentially to the crop in question. In this case, it would be turf. So in the Irrigation Association is a US-based institution, and they use something called a landscape coefficient. And this is just for concepts. I don't want anybody to get too hung up in the details, but this is the way an adjustment is made to reference ET to get to the amount of water you really want to apply. First of all, you have to look at the species of the crop. And that's, in agriculture, we use something called K sub C, or crop coefficient. In some turf applications, they call it a species factor in case of what the Irrigation Association terms it as. That's essentially the same thing as a crop coefficient. For turf grass, that's going to be anywhere between 0.6 and 0.8, depending on if it's a C3 or C4 turf and that sort of thing. Density factor, in this case, we can ignore and just set to 1 for turf unless it's very poorly managed. And then microclimate is another adjustment factor. If you cannot neglect shady conditions or conditions that are right next to arid conditions where actually energy or wind is being blown in and there's extra energy being applied over your area, and it'll actually have some aridity effect and increase the demand. And when we look at the irrigation water requirement, we also want to know how much rainfall we can expect so that we allow for that and then just make up the residual or the balance with our irrigation. This is just an example of what has come out in the publication. You can see the URL down here. If you just Google water requirements in North Carolina turf grasses, it may not be applicable to you, but it gives you an idea of how this problem is tackled. And in this case, a graduate student did a water balance, I think a daily water balance by month, and then looked at, based upon these mean temperatures and average rainfall and our reference ET here, we can come up with how much the irrigation requirement is needed for either cool season or warm season. You'll see here that warm season turf grass, as we can get away with applying less because it doesn't suffer from drought stress like the cool season turf would. And so we can, the crop coefficient rule of thumb is 0.6, whereas it might be 0.8 for C3 cool season grass like tall fescue. So you can see it varies.
Doctor, share your screen.
Share my screen. Okay. Where do I share my screen? I apologize for that. Is that better? Oops. That's the wrong presentation. Let's go to the other one. Oh, is that better? You see my screen now?
Okay.
Okay.
Perfect.
Do you want me to go back to the beginning or just start from here? I'll start from here. I think we can start from here. Okay. Now you see it still? Okay. Apologize for that. Anyway, as I was saying, this is just an example. You can see the kind of the methodology we use to get to a water requirement, an irrigation water requirement, which is going to take into account rainfall. Now we don't use all of this rainfall to subtract from the reference ET or the crop ET or the plant ET. We use something called it's effective precipitation. It's going to be something less than the rainfall. But we need to make up the balance not supplied by rainfall by irrigation. And here again, this is warm season, we'll need less than cool season to keep it looking attractive because just of the physiology of the crop or the turf. Another way to get estimates of water requirements, here you see a weather station we deployed in this study, and then we used the weather data in concert with an equation to come out with a reference of evapotranspiration. Another way to do it is using something called, it's a physical model called a atmometer. This is simply a reservoir of water that's attached to a tube and has a ceramic cup on top. And the ceramic cup leaks or weeps water based upon the atmospheric demand. So it simulates sort of like the stomata on a plant, and it wicks out, and then you can get a good idea of how much your reference ET might be. It mimics a kind of a turf canopy. Here, for instance, is on the y-axis, we see what we got with a reference evapotranspiration using weather station data, and this would be daily values. I think we're regressing here. Or versus ET gauge versus the weather station data. So here's the ET gauge. You fill it with water, distilled water. It wicks out through the ceramic cup, and there's a canvas filter, a canvas top on that, and it wicks out based upon atmospheric demand that simulates what the crop would use. And that's another way of estimating kind of a reference of evapotranspiration. You can see there's a pretty good relationship here. It's a little less. And when it rains, this cap gets wet and it suppresses evaporation. But if you look here, even if you had just something like an atmometer and a rain gauge, here you have one component of a water balance, the crop demand. And here you have another component of the water balance, rainfall. Now, not all of that rainfall collected will be affected. There'll be some interception by the canopy. There may be some runoff. But anyway, that's the idea and the concept of how we go about determining what is required through irrigation. I thought it would be kind of interesting. I went on and did some calculations for these three stations in Peru: Trujillo, La Molina, and Cusco. And what I did is I took some freely available software. CropWatt computes the Penman-Monteith estimate of reference evapotranspiration, and you can get that online. It's a Windows-based program. It's sponsored and done by the Food and Agricultural Organization of the United Nations. And in concert with that, they have something called ClimeWatt, which is also freely available. And that has hundreds and hundreds of long-term weather station data from all across the world. And I just pulled that weather station down for Peru and did these plots. So you can see there's a difference in elevation as we work from around the coast up into the Andes, Cusco at 3,200 meters. Now, what I plotted here for those three stations is crop ET, and that is derived by taking a reference ET, and I'm assuming a warm season grass, 0.6 for a crop coefficient or a species coefficient there, and arriving at that ETC. That's the red dots. Now, when I subtract effective precipitation, and the program does it for you, you get what's called the net irrigation requirement, which is the crop requirement less the effective precipitation. So it's just accounting, essentially. You notice here at Trujillo and also La Molina, because there's so little rainfall, they're almost coincident, the two values. However, when we get up to Cusco and there's an appreciable rainfall, you can see that the irrigation required is suppressed at nothing in some of these months and then rises when there's more demand and a little bit less rainfall. So that's that, it shows you the difference in rainy seasons and elevation for you. In a way, it's easier to manage irrigation in a location with no rain because you know what's not to expect. When there's a rainfall that is spatially variable and not very predictable, it makes irrigation scheduling much more difficult because you don't know when that rainfall is going to come and how to adjust your irrigation. Okay, so back to the adjustments to the reference ET. This species coefficient can range from anywhere from 0.2 to 0.9. Again, I would say here's a warm season grass. And we are not irrigating here, it's dormant. We're irrigating here just for uniformity assessment. I don't want to give you the wrong idea. This is warm season grass before it's greened up. We would assign that when it's greened up, probably a coefficient of 0.6, and that would derate it by 40% from the reference ET. Cool season grass over here, we might multiply the reference evapotranspiration by 0.8. And so we're going to put a little bit more water in this cool species and the warm season species due to their difference in physiology and their adaptation to drought stress. Microclimate, what I talked about, you see the shaded area, especially in smaller turf grass areas next to forested areas or even buildings, you're going to get a sufficient, fairly different requirement due to afternoon shading, which would suppress the water demand. So that's something I always take into account. If you're in a large open sports field, you don't have to worry about that. Again, so this was kind of an overall adjustment factor to the overall coefficient, the landscape coefficient. Again, don't worry about a density coefficient, set that to 1. Microclimate, you might account for shade. And species, we talk about that 0.6 or 0.8, depending on the type of grass. But don't get too worried about this because you're going to come in with a decent estimate and then adjust as you go. There's nothing to replace observation. And don't get too hung up in a lot of equations and a lot of minutia, as we say. So now another terminology. What's our gross irrigation requirement? We talked about the net irrigation requirement being the crop need minus the effective precipitation. Well, and on top of that, our irrigation system is not going to be totally uniform. And so we have to add a little bit more application to account for those areas that receive less than the average. And so typically we adjust by the DU low half. And because the DU low half is not decimal, we divide by 100 to get in decimal format. And so that will make it something less than 1. Therefore, our gross irrigation requirement will always be greater than net irrigation requirement. So there's no rain. You can just go use an ETC. If you have rain, then you're going to look at the net irrigation requirement. And again, the DU low half is a distribution uniformity of the low half that we talked about last session. You don't want to use, I would not recommend using anything lower than a 0.8 in the denominator or an increase in runtime of 1.25 because what you're going to do to satisfy dry spots is really over irrigate the other areas. So you should really cap this adjustment factor. Okay, so how do we measure soil water and what are some of the basic soil water sensor types? One is based on soil water tension. This is what's called a granular matrix sensor. In the old days, it used to be some things called gypsum blocks. These are a little more advanced, but what they do is electrically, it's an electrical circuit. And as this gets wetter, the resistance goes down. And so it transforms it from electrical resistance to a tension, a reading of tension. And that tension is in centibars, kilopascals. So it's similar to a tensiometer, and we'll see a picture of one of those later that's used in agriculture quite a bit. So it doesn't measure the absolute water content, it measures the soil water tension. The drier the soil, the higher the tension or negative pressure. There are other classes that just go directly and measure your soil water content in volumetric terms. And they measure electrically again. It's a dielectric constant. Electrical is a volumetric soil water content in a block of soil. This measures total water content. The sensors that are volumetric measure the total water content. So for instance, if we had 0.3 here, that's 0.3 millimeters per millimeter or 300 millimeters per meter. That's about 3.6 inches per foot. That's total water content. However, rule of thumb, only about half of that water is available to the plant. It cannot physically extract it. So the other term we have here is available or plant available water holding capacity. And that's the amount, in this case, about half of the total volumetric water content at field capacity that's available to the plant. So if you were to saturate a soil profile up, just totally saturate it, it would drain out the gravitational or free drainage, free water drainage. And that's just, that's drained out against the force of gravity. And for a sand, you would achieve that level in just a matter of hours normally. For medium texture soils and clays, it may be a day or two or even 3 days for that to achieve that level. Now, from within the plant available region here, we don't want to wait till we get down to the permanent wilting point before we irrigate. So another rule of thumb is that somewhere around the value when we have used half our plant available water, we want to fill up the soil profile again. So this is just a graphical display of terms and how we want to manage water. We want to measure it between these 2 points. We don't want to put out too much where it just drains away, but we don't want to let it dry out till we hit stress. So there's an increasing amount of stress as we dry down this water here that's available to the plant. So anyway, there's a relationship between soil tension and soil water content, and that's the difference between the two types of sensors we looked at. But here's an illustration of the matrix or soil water tension sensors, soil matrix potential. Excuse me, here. These are buried in a cotton field at 6, 12, and 18 inches or 15, 30, and 45 centimeters to look at the water content over depth. And these are watermark probes, which are only about 2 inches long, and they cost maybe $40, relatively inexpensive. And you can hook a cable to them, and we install them and put them in a 3/4 inch or 1/2 inch class 315 pipe. Fits right over the collar of the sensor and bring out the wires, and then we solder them to leads on top of the ground for this experiment and record the data. This is a tensiometer. It measures a physical suction in the ground, and as the suction is applied through the bottom of the porous cup buried, it drives that gauge to a higher negative pressure or a suction. They can only report to about 80 or centibars before it breaks section. So this has to be on the weather side when you're using these. You would not use this in a turf application, but it's a physical model of what this is electrically doing. Now in a sports field, I could see an application where you would take that sensor, bury it, then knife in, or with like some sort of a circular trencher, very narrow, lay a line up to hundreds of feet or 100 meters, and then use a meter to read the tension. Those meters are about $275 US. And they're portable. So you could have any number of these buried, and you could bring this to the edge of the field so it's not in the way of anything, bring it up and connect the leads to the meter and read it. These meters and this general application of soil water tension is really most beneficial to use as a set point. In other words, when it gets to a certain tension, it's time to irrigate. And then you can kind of calibrate the depth you apply by looking at the sensor afterwards and seeing where it came back to. Okay, a great option, and I think Mark Johnson yesterday talked about this, is a portable TDR probe. The great thing about them, they're portable. You can take samples wherever you want to. And evidently, I have not used one of these, but you can actually have it downloaded the software and you can map out water content over your area. And you can look at one point over time. You can look aerially at your distribution of water content. So I think you can hook this to some sort of a GPS device, or it has GPS on board, so you can get an aerial distribution. And so that's a really nice option, especially for the sports field, because it's non-destructive. You don't have to dig anything up to plant the sensor. You can just go in. Now the other cost is the probes, and so you might have the probes, I think we were talking about yesterday, go up to maybe 8 inches, and so it depends on where you want to get the reading from, or over what sampling volume you want to read from. If you have a lot of money and want convenience, there are wireless soil wire sensors. So the advantage of that, you don't need to bury the wires. They're accurate, they're good sensors. However, these are usually sold as systems and are generally proprietary, meaning that one company is going to try to sell you the whole system and it's going to be expensive. And usually they're not very easily mixed with other systems. So they tend to be expensive. We have had multiple companies come by that were developing these systems to NC State, to the turf labs, and have us test out these sensors. And one thing you have to watch out for these commercialized sensors is they will report in different units. They might say 100% or 50%, and they won't give you volumetric soil water content. So you have to be very careful on how to interpret their numbers. Again. Okay, irrigation controllers. Ultimately, you're going to have to program a controller to automate your irrigation. Unless you do it by hand, you can turn solenoids on by hand, but it gets a bit labor intensive. So there are controllers made everywhere from residential, light commercial, industrial. Here on this side, you see a Rainbow ESP type controller. You can hook these up if you're close enough to a Wi-Fi signal network. You can get on the local Wi-Fi, and then using your phone, you can make changes and to the controller remotely, and to golf course. And the difference with golf course is going to have many, many more zones, much more flexibility. Typically, each sprinkler head will have its own valve, or essentially be a zone unto itself. And you can also get weather stations to integrate with these systems such that it will, on the fly, generate a reference ET, go through some calculations, and then help you decide how much to apply on any given day. You must remember, though, on irrigation controllers, and I'm sure you're well aware of it, that the time you are allowed to irrigate may be very dependent upon what the use is for. If you're on a golf course, you want to be watering at night. If you're a homeowner, it may not be that restrictive. Parks may not want to water during the day, they're being used during the day. So these are all things to think about. Usually, when you program a controller, you might want to start with some sort of a base schedule. So you want to use your audit results or knowledge of your system to know the application rates, and how much you might want to adjust that for non-uniformity. And you estimate your plant requirement for a certain period, maybe a week or during a certain month. And then you just make seasonal adjustments. You can vary your run times as the demand goes up or down if you have a constant interval. Or you may want to apply that same depth and vary the frequency. Now, normally with simple controllers, you wouldn't vary the frequency unless you went in there every month or so and change that frequency. So you may want to vary run times. And now in some municipalities, you may be limited to watering on certain days of the week, in which case you have to stay with the same days, and then you would vary your run times seasonally as needed. Again, you must not overlook your looking observation and adjusting based on what you see. And rain switches are great add-on if you have a lot of rainfall, because they were prohibited irrigation when it's not needed. When it gets so much rainfall is collected, there's expanding corks or discs that will isolate a circuit and not allow the controller to irrigate. In some cities in the United States, they are in ordinances where you have to have them legally to operate a system, or at least you're supposed to. But for saving water, they're good. Okay, so how do you compute your run times? Well, you have your gross irrigation requirement millimeters, and you know your precipitation rate millimeters per hour, and then you multiply by 60 to get your minutes. That will be your runtime in minutes. I will say that most simple controllers may come with a default runtime of 10 minutes. And I've seen a number of controllers, like a lot in homeowners situation, where you go look and do an audit and the runtime is 10 minutes because nobody changed it from the default. So that's obviously not what we want to do. So if you know what your requirement is in millimeters, and then you divide by your precipitation rate times 60, that will give you the runtime. Or you can take your runtime in minutes, rearrange it, and get your runtime by using the net irrigation requirement over your precipitation rate. And that's if you have a rainfall situation. Net irrigation requirement and your gross irrigation requirement. Okay, okay. And another way to look at it is a runtime adjustment by non-uniformity. Again, as I said, you do not want to use, I think, anything lower than a DU of 80, even if you audit it less than 80. Otherwise, you're going to be, if you use 80, that's a 1.25 factor, and that's a 25% increase in your runtime. And you don't want to over irrigate most of the area just to satisfy the dry areas. Okay, so use caution anytime your DU is measured at less than 80. You don't want to plug in anything less than 1 or more than 1.25 on your runtime adjustment, or a DU here in this equation of less than 80. So let's look at an example for La Molina in February. So on the software I used, the net irrigation requirement is 70 millimeters for February. Let's say that we want to irrigate twice a week, and the DU of the low half uniformity assessment was 80. So we assume that our application, this would be from the audit, if we have an application rate of 20 millimeters per hour, and that may differ by zones. You want to be careful about that. The gross irrigation requirement is going to be net irrigation requirement divided by that uniformity factor here. So that'd be 70 millimeters for net irrigation requirement divided by 0.8. That gives us 88 millimeters to apply in February. If we're irrigating twice a week, that means we're going to have 8 events in the month. That's 88 divided by 8. So our target to apply is 11 millimeters per event. So to set a runtime, we simply take that 11 millimeters that we want to apply, divide through by 20 millimeters per hour, and then multiply by 60 to get minutes, and that ends up with 33 minutes to apply. Check here, we'll close this right now. Okay, so here's an example of what we did in a homeowner study in a local town. We knew the application rate by audits, and these are individual zones and the type of system, type of sprinkler that was in the zone, mostly spray heads, and here's a rotor zone. So we divided this up by periods where the water demand would be about the same. So here in North America, we had June, and then July and August grouped, and then September, October. So you'll see here, the longer run times are in the heavy demand period of July and August. And what we did, we went through that same type of calculation I showed earlier to provide the runner, the homeowner, with suggested run times by zone. So their charge was to, at the first of this month, for instance, go in and make runtime changes to reflect the water requirement. And generally that worked pretty well. If you have a simple controller and go in and adjust run times, chances are you will do almost as well, or just as well as a more advanced device such as the ET controller. Here's another example from this extension publication from North Carolina State that shows by month for Charlotte area, which is a large metropolitan area here in North Carolina, based upon your system's application rate. Up here, you go down and look at the runtime for each month to apply the gross irrigation requirement required for that month. Again, as you see, the runtimes go down as we get to a higher application rate. And this table is divided between cool season turf, warm season turf. So the warm season turf is going to have shorter run times compared to the cool season turf because of that species or crop coefficient that we applied earlier. So the other way to do it is you set a desired irrigation depth, which is our allowable depletion that we saw in that slide earlier. They had a column of soil. And we can calculate the number of irrigation days we have in a period and then back out our irrigation interval. So we have the net irrigation requirement over the period, and then we divide through by what we were going to apply to replenish that water, which is our allowable depletion. That'll give us the irrigation days in that period. So we have a net irrigation requirement at Loma and Lena in February of 10 millimeters. And let's say our allowable depletion, we let it drain, we let it use 10 millimeters, and then we refill that. Our 70 divided by 10 is going to be 7 irrigation events that we have to fill that requirement. And then we back that out 28 days in February divided by 7 would work out to be an interval of every 4 days applying that fixed amount. So we can have a fixed runtime, which equals a fixed amount, or we can have a variable runtime that we adjust by month. So different approaches. It may be that you're required to irrigate on certain days in which you're going to have to eventually adjust the runtimes. Let's look a little bit of look at some smart programs here, smart irrigation systems. Okay. So here you see just some examples of different, this is a Toro IntelliSense. I think they still make these. It actually uses remote data from satellite to do a water balance and come out and change run times based on the days you set. This is a system that has an on-site weather station, very simple. And this would be representative of the type of systems that use actually a soil water sensor to normally prevent an irrigation when it's too wet. So there's different methods. Especially for the ET systems, you need to know your system's application rate, because you can get off over the course of time if you program into the ET controller your application rate and you're putting on twice as much water as you type in. In actuality, the ET balance, they're not going to know the difference because there's nothing in the soil to provide feedback. It's just based upon a water balance from weather and what the assumed application rate is. So it's very important to know that when you use your ET controller. The other class of the two general classes again are those that use a soil moisture sensor to provide feedback, or weather-based controllers. And the weather-based controllers use weather data that's either collected on site, like this case, has a very simple temperature probe and solar radiation, and that's it. And it can compute from like a Hargreaves-Samani equation, a water requirement. And then actually, I think it's just temperature on this one. And it looks at latitude to give you an estimate of sunshine. And then the other option to go is sensors that are in the ground. It actually will regulate the soil moisture based upon thresholds that you provided. In this case, for this system, you program the volumetric soil water content above which you disable irrigation. You do not allow it to irrigate, it's too wet. In a sensor system, you can actually have a regular system, and these are going to be more like commercial, industrial, and homeowner systems without any change. And you put the sensor in, it acts like a rain switch in the ground. That is, it will prohibit irrigation when it's too wet in the soil, just as a rain switch will prohibit irrigation if it senses too much rain. And then you could vary your seasonal adjustments, your run times, as we looked at earlier. Or another way of approaching these systems is you program the system to run every day to replace the water loss at your set point. And then it will not allow an irrigation if it's above that set point. And then by setting the water every day, you're setting a high frequency, but it's only going to irrigate on the day that's hit that set point. And you would be essentially, you can irrigate a constant depth to replace that amount lost at that set point in volumetric water content. Some of these are complete systems. They all integrated. This brand right here that we used in research is no longer a company. They went out of business. So I would advise you, if you're considering any of these smart systems, to stick with a well-reputed brand because some of these companies come and go. This is a Rainbow system that we evaluated. And I will tell you from personal experience, in years past, we had a number of failures with these types of probes. I think they fixed them since then, but you always have to check on your system and make sure things are operating correctly. So in a sensor system, there can be two different ways of looking at irrigation. One is that you have a one set point system, and the other is you have a two set point system. In the two set point system, as you get to lower set point here, as you follow my cursor, initiates the irrigation, hits the upper set point, stops it. Then your turf uses it, irrigate up to the field capacity or whatever the depth you applied. Turf uses it, hits the threshold again, irrigates up to a set point. So those are the two different sets. The other one, this is an upper threshold here. You can set for an upper threshold if you do not want to get it too wet. So it can get quite confusing knowing how to select an ET controller. Some of them have on-site weather stations. Some have a third-party weather service. Some are add-on to an existing controller. Some are integrated into one system. And so there's all these variables. Some of them have web-based programming. They have different communication capability. So it's very important to do your homework before you select one. And you obviously want to consider cost and availability and support and service by the manufacturer. And never forget, if you have a client involved, that you need to meet their expectations. Okay, the ET sensor sites are kind of two different categories. You have on-site weather. This is a very simple system by the company named Hunter. It has solar radiation, temperature, enters it into a simple equation, and tells you and adjusts the runtime. So in this case, you would set the runtime to 100% for like the heaviest use period, and it would go up or down based upon the reading it has based upon the soil, based upon the solar radiation as input and temperature. So it would use something like what we call a Hargreaves-Samadi equation. Offsite weather, there's all sorts of different ways. So especially if you're in South America, you might want to find out first, can you have any telecommunications with a system, and make sure that's going to work for you. This system by Toro has a lot of input you have to give it. And the caution I would give you is that just because it has a lot of inputs doesn't mean it's going to be more and more accurate, because a lot of these are unknown. You may not know the root depth exactly. You may not know the location of the slope, but exposure, all of these are kind of a little bit of a guess. But you do have to enter into this, like I mentioned earlier, the type of irrigation, the type of sprinkler, or the application rate. You're going to be better off if you know the application rate, because if you enter the type of sprinkler, it's going to assume an application rate. They may not be correct at all. Okay, so let's proceed here. Okay, if you're going to replace water based on the set point, this is from the previous time, you just draw down your water to this volumetric soil water content and then run. And so this would be essentially your net irrigation requirement. You would convert that to gross irrigation requirement, divide through by your application rate in inches per hour or millimeters per hour, multiplied by 60 minutes an hour. And that would be your runtime in minutes to get it from this point to that point. Some are add-on controllers. This is a Hunter solar sync system that we evaluated. You simply take that and enter it into the port on a regular controller that has like a rain switch. And then you go through an interface that programs, and you tell it where you are in the world, and then you set your run times on the controller to 100%, and then you walk away. The Toro system here is a standalone system, so it's all integrated and goes to a third-party service. So again, this is just an example of one product, and I checked. I think they're still being sold. They may not be manufactured anymore. So that it takes that solar radiation and temperature data, and it actually changes your percent adjust key on the controller, thereby adjusting your run times. So here's actually a controller that I have communication with on my phone. Except I will tell you that this morning or yesterday it came off of the wireless network that was hooked to, and so I can't talk to it. So that's another thing to be concerned about. But you can see here, right now I'm renovating. So I planted some leaf fescue seed, and so I want to water it every day. And I can change that via my phone. But the smart part about this is this seasonal adjustment toggle. I slide this over and I've set my run times for the most demanding part of the year. It will adjust that. Now, I'm not real comfortable with this system because I have no idea what measures they're using to calculate reference evapotranspiration. And when I set my extreme run times at the beginning of the year, and we had some weather that was not the most extreme water use time, this number went to over 100%. That doesn't give me a really good feeling about what they're doing. And I think many of the systems don't account for humidity. So if you're in a high humidity situation where you have a high dew points and you have, that means your saturation vapor pressure deficit between your leaf surface and the air is not great. It suppresses ET. And a lot of these equations don't account for that suppression of ET due to humidity. So that's just one thing. However, it's very convenient to be able to sit at home and make adjustments to your controller. So this Rainbird system I just showed you, there's a little module you plug into a controller, and that's actually available in these South American countries. It's not in Peru, but it's in Argentina, Brazil, Colombia, Chile. So yeah, it is, Rainbird being a larger company and International has that option that I just showed you in some South American countries. And they're probably, being changed all the time. So you just need to keep apprised of that. Another example is just in North America available, but it's, you can program this over the internet. It gets weather data from a server. You input your application rates, your soil, your plant, soil type, plant type, and you enter your watering frequency that you want, and it will get the duration for you, or vice versa. These are generally not available for 2-wire systems. 2-wire system is those systems that are like golf courses and larger systems where solenoid valves are connected by common 2 wires in the circuit, and they're addressable. So you cannot use that on this sort of a system. And you have to have 24-volt AC valves, operating valves on this system. Just an example. These technologies and products are changing all the time. It's very difficult to keep up to date on them. With that, I'm going to open it up for any questions you might have. This is one of the controllers we evaluated. It's called the Weathermatic. That's the brand name. It's out of Texas, actually, and it was very good. It has an on-site sensor, very simple to program. It did very well. A lot of times, the simpler these systems are, the better. So I'm waiting for any questions if you have them.
Thank you very much. Susanna is not here to help us to make a question, but you have a question in the chat. Can you see the question?
Let me see. I don't see it. Let me just toggle down here. Okay. Interaction between fertigation and irrigation efficiency in grass in North Carolina. The more if you have proper fertility, grasses are going to grow more and then, slightly demand more water. Now, if you want to know about if you apply fertigation, I'm assuming that means if the irrigation is non-uniform, your fertigation is going to be non-uniform. Now, what I will say is that once it gets the water and the fertilizer gets in the ground, it will spread by major potential laterally and be better than what you catch in the can. And that's been proven through studies that your catch can uniformity is poorer than if I took a TDR probe and went around and took readings. That uniformity would be much better because once the water enters the soil, it does diffuse and spread through major potential and gravity. So it's going to be better when you look at it in the soil fertigation than it would be for what you see hit the ground. Water reuse. Okay. Here in a town nearby, there's actually a market. Well, actually, the municipality requires that you use their reclaimed water if you're on their line. It's high quality, nothing to worry about from a chemical standpoint. And it's, it's well worth using, and it's actually a cheaper rate because they don't charge you for sewerage here locally. But a growing market, yeah, when you don't have rain and you're limited on water supply, reclaimed water is a good option, especially if whoever the entity or utility is wants to use it in some way instead of putting it back in the stream. There are wastewater systems here in North Carolina that will actually be able to sell what credits, the nitrogen credits, by land applying their water, treated wastewater, instead of putting it back in the river. So you'll see wastewater treatment plants that may have land application systems because they can sell the nitrogen credits to keep them out of the river to someone else, and then by land applying it. So yeah, it's an emerging market. So usually the water quality is no issue with irrigation and water management, unless you have high degree of salts and you want to worry about that.
We're still waiting for another questions, but I think we have no more questions. I have one question for you. What are you thinking to use the water moisture content like TDR or like POGO to control moisture in the field, and also to make an audit irrigation using those kind of tools? What is your opinion about that?
I think it's great, especially portable probe, because if you stop and think about it, when you look at a water balance and ET estimates and all this other stuff we go through, ultimately what's important is what's in the ground. So conceptually, I really like the sensor controlled smart controllers, but then the downside is that you got a lot of these, you have to install wires, you have to hook up to solenoid valves, there's all these other things that make them less attractive. But if the audit, if you have a fairway or a sports field that is dried out sufficiently, you might want to take readings prior to and after irrigation and see how uniform your irrigation is. That's even better probably than looking at catch can data, because that's actually what's in the root zone. So yeah, it's a great way to go if you have some sort of probe like that, especially if you can get one that's you can spatially represent it with GPS or whatever you have on board, so you can get a good picture of it. Now here in North Carolina, we have wastewater irrigation, we have swine waste, and there's so much nutrients in that you can only put on maybe 75 millimeters of irrigation in a whole year. But that's kind of a waste disposal mechanism, and they put it on